it is all on. So good afternoon. Welcome to the third and last installment of the mini school on the DEX calculus. I think Kishan doesn't need any introduction anymore. You met him already for 2 weeks. And I missed the last lecture live, but I had the opportunity to catch up. And I'm very curious to see story evolves. Yeah, and Kishan, you're most than welcome to start. I just try to find a view full screen for you. Voila. And here you go. You're most than welcome.
Thank you. Okay, so this is the third and last lecture in this mini school. And in this lecture, I'll be speaking a bit about circuit extraction. So just to recap, at the end of the last lecture, we looked at some examples of measurement-based quantum computing in the sense that instead of simply applying a phase gate to a qubit in the state psi, we may alternatively write this or represent this diagram using this measurement-based quantum computing pattern as shown on the left. So the phase gate alpha here is equivalent to this diagram on the left here, where we are making a measurement with respect to the angle alpha. But some problems arise. We said that we might need to do some corrections in order to ensure that we do end up with this alpha phase gate. So this shows us that there are two models of quantum computation. The first is the usual quantum circuit model, where we have some qubits initialized in some state. We apply some quantum gates. So we can apply control knot gates, phase gates, Hadamard gates to proceed our computation proceeds via those gates. And then thereafter, we take a measurement to read our data. But we see that there's another approach, the measurement-based quantum computing approach, where our computation actually proceeds via measurements. Initially, we want to prepare our state in this case as well, and this is going to be a resource state, or something that we are going to refer to as a graph state, which I'll explain a bit later on. And in this model, we have to be slightly careful of this problem of correction to ensure that we get a deterministic outcome. So the measurements we will be considering is measurements in the XY plane, the XZ plane, and the YZ plane. These correspond to these spiders on the top row. And we said that measurements aren't deterministic. So if we are taking these measurements, we may get these undesired outcomes with the extra pi phase. So we need to account for these errors and correct these errors in some way. The reason for choosing measurements in these planes is because the corrections that we will eventually apply become our Pauli operators. So I did mention in this model, we are going to be initializing a resource state, or something that we call a graph state. It's going to be given by a diagram like this, where for each green vertex, we are going to prepare a qubit in the state plus. And for each dashed blue edge, we indicate a wire with a Hadamard gate on the wire. And this is nothing but our controlled Z gate. And this is a nice way to indicate the entanglement of our states. But these graph states also have a nice property that we get useful stabilizers of these states. So suppose this was our graph state with these vertices and edges. We have that this operator below here, where this xv, so we choose any vertex v, this xv is the Pauli x operator on v, and the ZWs here are the Pauli Z operator on all of the neighbors of V. If we apply this operator to the graph state is unchanged, and hence we call this operator a stabilizer of our state. we call this a stabilizer of our state, but let's get an idea of why this is a stabilizer of the state. So applying the Pauli X operator to V, so assuming V was the leftmost vertex, green vertex here, this red pi phase would be the Pauli X operator, and these two green vertices, the second and third vertices from the left, are its neighbors. So we need to apply the Pauli Z operator, which is given by these green pi phases. So the explanation below is saying that this diagram here is actually equal to the state that we started with. And the reason for this is that if we take this red pi phase and pull it through the diagram, the pi phase copies to the two remaining edges coming out of the first vertex V. And if we recall that these dashed blue lines have a Hadamard gate on them, if we pull it along the Hadamard, the color changes to green pi phases, and we can move them up and use them to cancel out these two green pi phases, and hence get the starting diagram. So this idea is going to be the central idea on how we want to correct our undesired outcomes of measurements. However, we won't always be able to take a pattern of this form and implement it, in the sense that sometimes corrections are not possible. So the first thing to note is this is something that we are going to call a measurement-based quantum computing pattern. The vertices, the lower vertices here, have a wire going into them, so we're going to call them the inputs, and the vertices at the top with the lines coming out, we call them the outputs. And why do we say that this is not deterministically implementable? Suppose we have this pattern and the alpha measurement had an extra pi phase here for this alpha measurement. To correct it, we'd need to use its neighbors, so the upper two vertices, to correct it. One of the upper two vertices, and that's how we would correct the first measurement. However, then if we were to do the second measurement for corresponding to the beta angle, we'd have to use the same vertex that we used for the first correction or the other one, but in both cases, when we are correcting for beta, it's going to affect what happened to alpha, because remember, when we applied the pi phase to correct, we pull it through and it's going to go down to this vertex that we measured initially. So this is why we say it's not deterministically implementable, as future measurements are affecting outcomes of the previous measurements, and we don't want this to happen. And just a remark that when we say deterministically implementable, we want this to have the technical meaning that this pattern corresponds to a completely positive trace preserving map, or in other words, it maps pure states to pure states. So we want some way to ensure that these patterns are deterministic, and hence we introduce the notion of a labeled open graph. So we are going to convert our pattern to a graph and label each vertices. We want to keep track of what's an input and output. So on the graph on the right, I've drawn inputs as squares and outputs as solid circles. And then lastly, we want to track in which plane we are measuring. So X, Y, X, Z, or Y, Z, corresponding to the colors of the spiders. And just another note, we cannot measure our output spiders. So this function, lambda, that tells us in which plane we are measuring, goes from the complement of the output set to these three planes. So once we have this, it's that structure is not enough to guarantee that our pattern is deterministic. We need some type of flow structure. So one of the sufficient conditions for determinism is called causal flow. And the basic idea of this is, for each measurement, we are going to assign a single qubit that we want to use to correct any undesired outcomes of this measurement. And another thing that causal flow needs is an order in which to do your measurement. So the formal definition is we have a labeled open graph where all the measurements here are in the XY plane. And we say that this graph has causal flow if there's this function here from non-output vertices to non-input vertices and a strict partial order such that there's a symbol missing that u should be adjacent to f of u. This simply means that f is the function that assigns the vertex that we are using to correct for measurement on a vertex that's not an output. So we want the vertex we are using for correction on u to be adjacent to u itself. The next condition is that we need to require that u is measured before f of u. So this strict partial order here is showing us in which order to do the measurement. And here we want u to be measured before f of u. And lastly, we want u to be measured before all vertices v that are neighbors of f of u apart from u itself. This is because all the neighbors of our correction vertex have some pi phase that slides to it. And if that was measured before u itself, then we are going to get measurements affecting outcomes of past measurements, and hence it would not be deterministic anymore. So let's look at an example of this. So an example of causal flow is this example on the extreme left here. So this is a pattern. We have 3 measurements here. The order we want to measure in is simply the linear order of 1, then 2, then 3, and then 4. Which vertices are we using for correction? So what is the function f? Correction on 1, I'm going to use vertex 2. For correction on 2, I'm going to use vertex 3. And for correction on 3, I'm going to use vertex 4. How do we actually do these corrections? Suppose I got an extra pi phase on the alpha measurement, then to correct it, I put a red pi phase on the beta measurement. And when we actually do this correction, we slide the red pi phase on beta to its 2 neighbors. It cancels out with the extra pi phase on the alpha measurement or the alpha spider. And it also goes to its other neighbor, namely the gamma measurement. But this is fine because by the order of measurement, we have not measured gamma yet, so this is still allowed. And a similar thing happens when we get an extra pi phase on the beta measurement. There's a green pi missing on the beta spider here. But that's not the full story, because there are deterministic patterns that don't have causal flow or C-flow. Examples of this would happen when our measurements are not all in the XY plane. Or we could also have deterministic patterns where more than 1 qubit is needed for corrections from a single measurement. So as an example of this, we have this pattern on the slide here, where we have 3 measurements, alpha, beta, and gamma. It turns out for this, I'm not going to go through the complete explanation. Suffice to say that no matter what order we choose, if for the first 2 measurements, you can always correct it using one qubit, but for the last one, it's impossible to correct it using just 1 qubit. However, it's still deterministic, and I'm not going to explain fully why it's deterministic, but towards the end of this lecture, we'll actually see it's deterministic and extract a circuit from this exact pattern. So to account for the case when we need more than one, qubit to correct, or we have measurements that are not just in the XY plane, we have the notion of generalized flow or G flow. And it's defined quite similarly to C flow. However, because we are allowing for many correction vertices, we have more conditions. So we have a labeled open graph. it's said to have generalized flow if it has this strict partial order on my vertices. And we are thinking of this as what is the order in which we need to do our measurements. And we have this map G that goes from non-outputs to subsets of inputs. So instead of assigning a correction vertex to a single vertex, we're assigning a correction set to that vertex. And these are the conditions we need. Firstly, we need to measure V before all vertices used to correct it. Secondly, if W is in the odd neighborhood of G of V. So the odd neighborhood of a subset is going to be the set of all vertices that are adjacent to an odd number of vertices in S. And why do we consider something like this? So if you look at vertices that are connected to an even number of vertices in your correction set G of V, they will have an even number of pi phases that slide to them. And an even number of pi phases will always cancel out. However, if they're adjacent to an odd number of vertices in your correction set, then these are exactly the vertices that get the extra pi phase. So for all these vertices W, getting this extra pi phase, we want either W to equal to V or V must be measured before W. Because if this weren't true, then we'd be affecting outcomes of past measurements and it would not be deterministic. And then these last three conditions account for the fact that we could be measuring in either of the three planes. So for the XY plane measurements, we want V to be in the odd neighborhood of the correction set of V. And this is due to the fact that this odd neighborhood of the correction set are precisely the vertices that get the extra pi phase, but these are the ones that get the green pi phase. And for the YZ plane measurements, we want V to be in G of V to be in the correction set itself, because G of V are precisely the vertices that are going to get the extra red pi phase. And we don't want it to get the green pi phase, so we also require it to be not in the odd neighborhood. And lastly, for the XZ plane measurements, we wanted to get both the green and red pi phase. So we wanted to be in the correction set and in the odd neighborhood. And that is why we get these last three conditions. But let's look at a basic example of this, which was the pattern we showed earlier, which I said was deterministic. This pattern actually has G flow because we can define our function G. So the measurements are happening on 1, 3, and 5. So what is the correction set for vertex 1? It's going to be this vertex 2 here. For vertex 3, we're going to use vertex 4 to correct it. And for the last vertex, I said it's impossible to choose just one vertex to correct. So we need to choose 2, and the 2 that we'll need are the vertices 2 and 6. And for these correction sets, what are the odd neighborhoods of these correction sets? So the odd neighborhood will be precisely the vertices in my graph that are connected to an odd number of vertices in the set here. So which for the odd neighborhood of the set 2, it's which vertices are connected just to itself, because the only odd number of vertices that I can choose from the set containing 2 is just 2 itself. So the vertices connected to 2 are just 1 and 3. Similarly, the odd neighborhood of the set containing 4 is just the vertices that are connected to 4. So that's going to be vertices 3 and 5. And the odd neighborhood of the set containing 2 and 6, it's going to be the vertices that are connected to either 2 or 6, but not both. And this is precisely vertex 5. And now the order in which we want to do the measurements, so here we just want to go from left to right. So 1 is less than 3 is less than 5. This does ensure that the graph has G flow, because we see that all the conditions are satisfied. In this case, we have only XY plane measurements, only the green spiders. So in each case, we want V to be in the odd neighborhood of G of V. So we do see that 1 is in the odd neighborhood of G of 1. 1 is in here. We do see 3 is in the odd neighborhood of G of 3. It is in the second odd neighborhood that we calculated. And lastly, 5 is in the odd neighborhood of the set containing 2 and 6. So we do have this 5 here. And the other condition that we would have needed to check is conditions 1 and 2. But I think this is not difficult to show that these order relations hold based on this definition of G and working out these odd neighborhoods. So this has G flow. So now that we have seen, in fact, in the last lecture, that we can convert our ZX diagrams to measurement-based quantum computing patterns, we know how to ensure that these patterns have determinism. And in the last part, we'll actually show how to go from a pattern with flow conditions back to a circuit-like pattern. But what was the point of this? The point is that once we convert to a measurement-based quantum computing pattern with flow, we want to optimize our pattern to make quantum computing more efficient. And hence we need to have some ways of simplifying our pattern that preserves these flow conditions. So the two main properties here that preserve flow, the first one is called local complementation, where to this pattern here, we have this extra red minus pi over 2 phase, and the edges are toggled in a certain way. And the edges are toggled in a way that comes from an operation called pivoting on this underlying graph here. But I'm not going to go too much into detail on optimization. The other important property is called Z insertion or deletion, where if we have this red A times pi phase connected to this middle here, it actually cancels out and these blue dashed edges, and here A can be 0, 1. So those are the main things that we want, the two main rules that we want for optimization. And in fact, for a variant of ZX calculus called stabilizer ZX calculus, which is precisely when all phases are multiples of pi over 2, we can show that all rewriting can be done using these two rules here, as well as the remaining rules for stabilizer ZX calculus, which were the rules that we defined as ZX calculus. So once we've optimized our pattern, we want to recover a circuit-like pattern from a measurement-based quantum computing pattern. So I'm starting with this example that we've been working with. We've shown it has G-flow. So how do I go from this pattern back to a circuit-like pattern? You start with a pattern. The first thing you do is you fuse the spiders. So this alpha, beta, gamma measurement spiders, we fuse them to get the second diagram. Once you have this, we want to now use controlled NOT gates to add or delete these blue dashed lines in a certain way. And I'll explain how it does that later. But essentially what we are doing in the next step is adding two control NOT gates, and these in fact cancel out. So we are not changing the diagram. So once we have these two control NOT gates, the one of them toggles certain blue edges here, and we get in fact more of these dashed blue edges in the next diagram in the bottom row. But now we see we have two dashed blue edges between certain vertices, and if we have two dashed blue edges, we can in fact remove them, and this is in fact a variant of the Hopf law for ZX calculus for these types of patterns. So we remove these parallel blue edges to get the next diagram. Once we have that, we have this diagram on the left here. What we now want to do is we see this alpha spider here. We want to fuse it to the rightmost green vertex that it's connected to via this blue dashed edge. And if we do that, we recall that this blue dashed edge has a Hadamard gate. So when we do this fusion, we get this Hadamard gate moving vertically up from the vertex that we fused to. Thereafter, we see that this alpha spider still has a dashed blue edge connected to it. So what we then do is unfuse vertically, and then instead of the dashed blue edge, it becomes this control Z gate if I indicate the Hadamard gate. And then lastly, we do the same thing that we did for the alpha spider for the beta and gamma spiders. So if I'm starting with the beta spider, I fuse it, and the Hadamard gate moves upward vertically on the wire to get the diagram on the bottom. And once we have that, there's still the dashed blue edge. So we unfuse vertically and represent that dashed blue edge as a controlled Z gate as done in the middle diagram. And then lastly, this gamma spider can be fused, and the yellow Hadamard gate moves upward vertically. And now this is something that we can see as a circuit-like pattern, as you can implement it using just some swap operations, some phase gates, Hadamard gates, and control NOT gates, and it's clear that this is a circuit-like pattern. But what I did just now, there was no method that I've described to you. I just showed you that this is what happens. But in fact, there's a method to doing this. Why did I choose certain vertices to put my control NOT gate? Or how did I choose that? And how did I know which edges appear or disappear? So this comes from a matrix representation. Now for this slide here, I'm reading diagrams from left to right. And if I have this diagram here, where this middle part here is the unextracted part, or the part that we are trying to make circuit-like, what we have here is this vertex V and its correction set identified. From this, what we then want to do is draw a matrix here. We are calling this a bi-adjacency matrix, and the rows will correspond to your vertices in the correction set G of V. So we'll have W, W prime, and W double prime. And for the columns, I'm going to have all of the neighbors of W, W prime, and W double prime. So we'll have V, U1, U2, and U3. And then it's actually, it's a theorem that if you apply a controlled NOT gate to a vertex W in the correction set, so we have a control NOT gate with control W and target, this here will be W double prime. What happens is in the matrix, the resulting bi-adjacency matrix will have the same effect as adding the row corresponding to the target to the row corresponding to the control. So we'll add the row corresponding to W double prime to the row corresponding to W, and that will give us our new connectivity conditions in the resulting diagram. And we can see that it toggles some blue dashed edges. And then we can do an extra control NOT gate with control on W and target on W prime. And if we do both of these control NOT gates, we see how these blue dashed edges are removed. And just to formalize that last property of when we are doing fusion, the Hadamard gate moves upwards. So if we have our extracted and unextracted part, we have this alpha spider connected to a vertex V. To move things to the extracted part, what we do is fuse alpha to V and then push it upwards. If we push upwards the alpha, we can move it to the extracted part to have an alpha phase gate and a Hadamard gate that moves vertically above that. So that's where I'll stop with circuit extraction. The full algorithm, I'll leave a reference if you do want to read that. But instead of doing it this way, there is a more general algorithm where we choose vertices in the frontier. So the frontier is the vertices that are just before the extract part, and you look at its neighbors and form one big bi-adjacency matrix, and then do this, do Gaussian elimination actually, and then that would obviously reduce your matrix, and hence what we actually do to the diagram is do the corresponding operations by adding control NOT gates, etc., to the graph, to the pattern to remove these blue dashed edges. And one thing I forgot to mention was when I mentioned add rows together, we are always adding modulo 2 because we are working with connectivity. It's always modulo 2. So that's how you would be able to generalize this diagram. And it's the analog is something like Gaussian elimination. So that's where I'll stop. And just to remark that I've just touched on a few aspects of ZX calculus, but there are many applications in machine learning, quantum error correction. There's in fact an extension of ZX calculus called ZXW calculus, where we have additional W spiders. And this has applications in topological quantum computing, quantum field theory, and quantum chemistry. And also there's active research in quantum natural language processing. And I'll just leave some references for circuit extraction on the slide here. And one of the main papers is in this topic that I used was this first reference here called There and Back Again, a circuit extraction tale. And I'll stop here.
Yeah, no, thank you very much, Kishan. That was another exciting lecture. And we have a plan for another 7 or 8 mini schools. Yeah, so thank you very much. Are there questions for Kishan? So any questions from people here? Any questions from people online? No, Kishan, in the just a stupid question, yeah, probably. In the here, sorry, is there any extension that would allow you to apply to some kind of open quantum systems? Because you already have the open graphs, you have the measurement based, and that's you're almost there.
Okay.
Yeah. Has anyone done something like that?
No, I haven't seen anything like that, but I'm not sure, to be honest. But I think it would be
But that would be very interesting because we could really close the circle.
Yeah.
Excellent. Okay, it looks like everybody needs some time to digest it all. Yeah, yeah. So Kishan, again, thank you so much. I'm sure Donovan and company will start to use that calculus immediately this afternoon. Yeah, and use it. Yeah. So thank you also to the online. There's something in the chat. Okay. Thank you very much, Kishan. It has been great from Elena. Yeah. Thank you, Elena. Yeah. So we will, I think today, tomorrow, we will announce the next mini school. And yeah, and thank you very much for being with us. Yeah. Thank you.